Great. Welcome, everyone. Like you said, I'm Wilco van Beijnum. I'm a volunteer at the Dutch Institute for Vulnerability Disclosure, where I research energy systems, and I also work as a cybersecurity expert at ELA.nl, and here I test EV charging stations on cybersecurity. Overall, I have 21 CVEs on my name already, and many other vulnerabilities discovered that were disclosed not publicly, but privately. A bit more about the DIVD. We also have a stand downstairs, so if you're interested, come find us there and we'll tell you more about it. But we're a foundation, a Dutch foundation that does vulnerability research and vulnerability disclosure, responsible disclosure. And we're also a CVE numbering authority, so we can also write out CVEs. So if after this presentation you use this knowledge to find any vulnerabilities and you want help with the coordinated vulnerability disclosure process with the manufacturer of a device, you can always contact us and get help. So, question at the start. Who of you has some kind of smart device at home, being a smart light bulb, smart thermostat, EV charging station, heat pump, whatever? Quite some hands. All right. So, have you ever thought about the cybersecurity of these devices? Well, maybe not. But these smart devices are often based around a couple of the same chips that are cheap microcontrollers with some kind of wireless connectivity support. And one of these controllers is the ESP32. You can see it here. This is one of the models of the chip. There are many versions, but this is one that I at least have encountered the most. And you can find chips like this in many smart devices. And today I'm going to tell you a bit about how these devices can maybe be hacked, and at the end also how you can protect them against it. And this ESP32 device is developed by Espressif. It has Wi-Fi connectivity, often also most versions have Bluetooth connectivity. So they're a really easy and cheap chip to put into smart devices, to give them this kind of connectivity, to connect to the cloud, connect to an app, that kind of stuff. So you see these devices, these chips used a lot in IoT devices. Today I'm also going to show some practical demo elements. I haven't brought an actual IoT device today, but instead I've brought an ESP32 dev board. So you can see here the actual ESP32 chip on the dev board, but this dev board adds some extra stuff such as a serial to USB converter and so on, which makes my demo a bit easier than bringing an actual IoT device, but we will get into more detail about that later. I've loaded up this ESP32 with some custom firmware that simulates some part of IoT devices, namely cloud connectivity. So this device performs a request to a cloud server, and our goal for today will be to try to find out what this communication is exactly. And then ultimately our goal would then be to look into this communication further, and the extra knowledge we gain can then be used to either look for vulnerabilities in the cloud server or in the device itself. For example, you could intercept an API key that you can then use to investigate the cloud, that kind of stuff. So what are we going to do today? Well, we're going to go over 5 steps. First of all, we're going to look at what the default behavior of the device is. So we're going to inspect some elements of that. Then we're going to dump the firmware of the device, so we can then analyze and reverse engineer that firmware. Then we're going to actually modify that firmware to change its behavior. And then finally, we're going to upload that firmware again onto our ESP32 and check if our patching was successful. And hopefully everything will go that way. All right, so let's start with the inspection part. So the ESP32, like I mentioned, has several interfaces. Well, one of them is Wi-Fi. to investigate the Wi-Fi communication of the ESP32, you can simply configure it to connect to a hotspot, for example, on your laptop. And then, well, at the basis, you can run a tool like Wireshark to just look at the traffic. Hopefully you will at least see that TLS is then used for the connectivity. And if this is the case, then you can also try to execute a man-in-the-middle attack on that traffic, the TLS traffic, to try to break into that and see if the device properly validates the certificates of the server when using TLS. And another thing that I mentioned was Bluetooth connectivity. We're not going to look into that any further today, but I do want to mention that if you have a device that uses Bluetooth, you can use your mobile phone and turn on Bluetooth snooping, and this will save a log of all the Bluetooth messages. So for example, if you have an IoT device with an app, you can change some settings and then pull that Bluetooth traffic off your phone and analyze that in Wireshark. Or if you have a rooted phone with ADB, you can even see the live traffic in Wireshark. And finally, an interface we're also going to look at today is UART, or a serial communication. And this is where often debug information is logged to. So this way we can intercept that communication and maybe use that to ease our reverse engineering. And for that we have an RX and TX pin on the ESP32 highlighted on the right there. For our dev board, there's also already a serial to USB converter on the dev board, so we don't need to do anything complicated there. But on an actual IoT device, you would have to solder some wires to there and connect that to a serial to USB converter to get that communication. So let's start with the demo of intercepting the network traffic and the serial output. So for trying to intercept the network traffic, I'm not going to look at Wireshark for now, but I am going to try to execute a man-in-the-middle attack. So I'm going to power on my device. I've already set up a Wi-Fi hotspot on this laptop. And if we now start mitten proxy, if we're lucky, we would be able to see the Wi-Fi traffic in here decrypted. But in our case, it says the client TLS handshake has failed because the client does not trust the proxy's certificate for example.com. So in our case, the device does properly validate the certificate, so we cannot use mitten proxy to intercept the traffic. And we do now know that at least the device is communicating with example.com, and we could use that information to, during our reverse analysis, reverse engineering, to look up that domain. Then we can also look at the serial output, and if I just reboot the device, we can see that we get some debug information when the device starts up, like the partition table and some specifications of the device, but ultimately we get a line saying disabling further logging, and we don't see anything anymore. Maybe also nice to know this presentation is based on actual IoT device that I investigated and found several vulnerabilities in, and we saw this exact kind of behavior on that device. So this is actually quite a realistic scenario. So now that we know how the device behaves by default and we don't really have much to go on, our next step would be firmware dumping. So let's get started with that. There are several ways to dump the firmware on an ESP32. By far the easiest way is to boot it into the bootloader and then pull the firmware via the serial interface, so the UART interface. For that, you need to pull GPIO 0, highlighted on the right, to ground, and then reboot or repower the device, and then it will boot into bootloader mode, and then you can send it commands, such as the command to dump its flash. So that's quite easy, and on this dev board there's a button for there's a boot button to connect GPIO 0 to ground, so that makes it even easier in this case. And then, like I said, you can connect to RxTX with a serial to USB converter like this one. and then use ESP tool, which is a tool set developed by Espressif themselves to dump the flash. In case you have some problems with this, you can also dump the flash directly from the SPI flash of the ESP32 or use JTAG to dump the flash, but we're not going to get into that today. So let's see how that works exactly, the dumping of the flash. So I'm just going to close this. And then we can simply execute the read flash command using ESP tool. And it will now start reading the entire flash of the device. I can maybe zoom it in a little bit more. So we see that we give the command to read the flash from address 0 all the way to the end and save that in firmware.bin, and that's what it's doing now. So I will continue the presentation while that's dumping, and then hopefully when we're at the next demo session it will be finished. So reverse engineering, our next step. So we now have this giant firmware.bin blob, and if you throw this into Ghidra, you need to specify a lot of information because Ghidra doesn't really know what this file is, what the CPU architecture is, how the file is structured, and so on. So to make our lives a bit easier, before throwing this into Ghidra for analysis, we can split this binary up into its different partitions. You already saw during the bootlog that there were several partitions defined. For example, at the start, we of course have the bootloader that's responsible for loading all the rest of the code. Then we also have a data store. That's a key value store that might contain things like API keys, so that might be interesting to look at on devices. We also have the factory partition, which, like the name implies, is the code that was put onto the device from the factory. And then you can also have 2 OTA partitions, which contain potential over-the-air updates. So if your device was ever updated via the app, for example, then one of these partitions might contain the latest version of the code. But in our case, we only have the factory partition and the OTA partitions are empty. So we're going to, after splitting up these partitions, open that file in Ghidra and analyze it. So let's have a look at how that works. So we now have our firmware.bin file in our directory here. So we can use a tool called ESP32 knife, which is developed by BlackVS, and we can use that to split up our partition. Let me just look for the command. There we go. So we give it the chip. In our case, it's a normal ESP32 version, and we're going to load everything from a file. And then you will see that it starts splitting out all the partitions. So at first the bootloader, and then also all the other partitions that we saw during the boot process. And it will dump all of these files into parsed. So we see here that we have this MVS partition that contains our key value store. In this case, there's not really anything interesting in there, but it stores that in several formats to easily read that. But most interestingly for us today, we also get this ELF file for our factory partition. And this ELF file contains a lot of extra information that can make it a lot easier for Ghidra to parse and analyze this file. So we're now going to open up Ghidra. Close this one. And we're going to load in that ELF file. So we have in our parse directory the ELF file. So if some of the text of Ghidra is a bit difficult to read, I tried to increase the most font sizes I could, but Ghidra is not the best on these kinds of screens. So now that we loaded the ELF file, you see that Ghidra has automatically from the file read that we have the Extensa architecture, which is the processor architecture of this ESP32. And you can also see that all the base image offsets and so on are also already defined. So this saves us a lot of manual configuration. So we can open up that file. And we can, now Ghidra asks us first if we want to start the auto analysis. But before we do that, we are going to skip that and run some scripts to further improve the analysis. So we're going to click the green arrow at the top, which is maybe a bit difficult to see. And we're going to run two scripts. First of all, we're going to run svd loader. And an svd file is basically a description file of a hardware device. So in this case, an ESP32, but you can find it for various other common microprocessors as well. And this file contains basically a description of some of the hardware addresses and a description of what is at that hardware address. So for example, this ESP32 has a lot of GPIO, which is memory mapped. So certain memory addresses map to a certain GPIO pin. And this file basically contains these mappings. So Ghidra can nicely label them. Then next, we're going to also run the symbols. The import symbol script. The ESP32 has a section of read-only memory that contains common libc functions. So these libc functions are not uploaded with your user firmware, but actually stored in the read-only memory of the device. So you can see that that contains things like free, calloc, write, all these common C functions. So if we and this file that we just loaded contains a mapping of the read-only memory address that the function is at to the actual name of the function. So if we would not load in this script, we would just get pointers to random memory addresses instead of a nice label of which function is called. So now that we've loaded in all of this, we can actually start the analysis. So we can run auto-analyze and start analysis. I'm going to skip that now and jump to a project in which I have already done that, since the analysis takes a few minutes. So that is this one. So after the analysis is complete, we get a view where on the left we see the decompilation or the disassembly, of the firmware. So the assembly code, and on the right we see a decompilation in a C-like format that Ghidra is able to infer from the bytecode. So what I often start with in this case is looking for strings. So for example, when investigating a network device, we can search for something like : to find web addresses in the firmware. Or in our case, we already knew that it was connecting to example.com, so we could also type that in. And then we find a string that is defined here. And then we can see where that is used in the firmware. So then we can locate probably the section of code that is responsible for making these web requests. And because we saw during our initial investigation that the device is using certificate pinning, we want to ultimately intercept this Wi-Fi traffic, and for that we need to break this certificate pinning, so disable it, and that can probably be found somewhere near the code that is responsible for doing the actual web request. So we can go to the cross-references and see where this string is used. So if we click through a couple of times, we get to this function. And we see that Ghidra has not automatically marked this as a function, so we're just going to do that manually by pressing F. And now we can start renaming stuff and reverse engineering it. So I'm going to make the right view a bit larger. One last script we can run to improve our analysis is the detection of logging strings. From experience, I know that this is a logging function. But we don't see the actual logging string here, but just a pointer to a data address, because Ghidra has some trouble automatically recognizing the logging strings of ESP32s as strings. So for that, I've written a small script that identifies all the logging strings. So after we run that, we can see that we can now see the logging string here. And if we click through to that, we see that this says certificate check is, and then something. If you're familiar with the formatting of logging strings, you will know that then the last parameter in this log will be the value that is formatted in there. So let's rename this to search check is. And we can see that this variable is assigned up here and is assigned the value either disabled or enabled based on the value of ifr 1. So by tracing this back, we can find the function that is responsible for finding if the certificate checking is enabled. So let's rename this to check certificate, and if that is false, then the certificate checking will be disabled, and we see that that originates from this function. So thinking forward to our patching, something we could do is just remove this function call and replace this with a static value of 0. But something else we could do is replace the contents of this function, because this function might be used in other locations as well. In our case, for this firmware, this is not the case, but I have seen firmware of devices where web requests are made from multiple locations, and one common function is responsible for checking if certificate checking should take place. And we see some idle function here that is inverted. So let's rename this should not check cert for now. And then we can also look at our logging. So we saw that ultimately something like disabling further logging was mentioned. So we can just search for this string, disabling further logging. And now you can also see that if we were to be able to enable the logging, then we can then use that information again to ease our reverse engineering process, since we can connect these logging strings back to certain functions that log these strings. So we can see where that is used, and we find this function, and right here we have the logging statement where the disabling further logging is logged to the device, but only if ifr1 is 0. So let's rename this to should enable logging, and if that is false, then the logging will be disabled. And if we click through to this function, we actually encounter our should not check cert function again here. So apparently this is a common function. So let's rename this to something like is debugging enabled. And this structure of functions is actually something I did encounter in an actual device as well. So I just recreated that code. And now we have this is debugging enabled function, and if we change this from return 0 to return 1 during our patching, we would in one we had two birds with one stone, and both enable logging and disable certificate pinning. So let's get into that, the patching part. So how can we patch the firmware of the ESP32? Well, of course, we now have the assembly, the disassembly of the firmware, and we can simply change that assembly code to something else, and Ghidra can actually help us with that. But after we do a search replace on a simple byte string and upload this to an ESP32, you will actually notice that this will not work, because the ESP32 after each code partition has a CRC checksum and a SHA-256 hash, which validates if the partition is well, not corrupt. So we actually need to change these CRC and hash values according to our new code. And for that, I've also written a Python script that can patch these values so our ESP32 accepts our patch. So let's have a look at how that works. So Ghidra actually has a nice feature to patch instructions. But before we do that, let's copy the original bytecode of this instruction. So we can copy that as a Python string. Let's see, Python byte string. And this will be our search. So we're going to search for these bytes in our original firmware.bin file. And we're going to replace that with some different bytes. So this will be our search. And then we want to make sure that this returns 1 instead of 0. Just to quickly walk you through what this assembly code does exactly. At the top we have an entry call, which is basically on the top of every function on the extensor architecture. We can just ignore this one. It sets up some stack stuff. Then we move the value 0 into register A2, which is the 0 that is returned here ultimately. Then we truncate that value to 1 byte or 8 bits, which is not really relevant in this case. It doesn't really do anything, but we can just leave that alone. And then ultimately we do a return call, which returns the register A2. So all we need to do actually is to change this value from 0 to 1. So we can patch that instruction, accept the warning, and then sometimes it has some trouble. There we go. We can change that to 1, and you see that Ghidra can automatically assemble this again and give us the bytes of that instruction. So if we change that, we now have our new bytecode, and we can copy this again as a Python string, and this will be our replace. And in this way, you can replace other functions, functionality as well, if you want to. So we now have our search and replace in this script, and we can save that and run it. So we go to our firmware patcher script, run that on the original firmware binary, and you will see that it does a replace, and then it checks the hash and the checksum of the factory partition, and it sees, hey, this checksum and digest are not correct. Let's update them. And for the OTR partitions, you see that these partitions are empty, so it just gives some errors there, but we can ignore those. So now we have our firmware patched.bin, and we can now validate that that actually works. So last step, we're almost there. Validation. This is quite similar to the dumping of the firmware. We just need to get our ESP32 into bootloader mode again, and then we can use ESP tool again to flash our new firmware onto the device. And then hopefully we'll have success, and we will be able to see all the logging strings and be able to intercept the network traffic. So let's see if that will be the case. So let's go back here and write the firmware patched file to the ESP32. We'll have to be a bit patient with this. Luckily it goes a bit faster than the downloading of the firmware. And after it is done flashing, we can start mitten proxy again to see if we can now intercept the network traffic. Just restart my server just in case. So now that the uploading is done, we can start mitten proxy again. And let's just reset the device. And if we have success, yes, we can now see our network traffic and our secret data that is sent to the server. And if this were an actual IoT device, like I mentioned, you would be able to extract things like API keys or valid endpoints, stuff like that, to maybe pen test the server that is that the device is connecting to. And we can also have a look at the logging again and reset the device. And we see now that indeed a lot more stuff is being logged. And this is very useful for further vulnerability analysis of the device itself. Since, like I mentioned, you can now, for example, we see more requests related to the network traffic here, and we can then look up these strings again in our firmware to find the functions that are responsible for that. So, for example, if you want to investigate the Bluetooth communication of a device, we can then do some actions in our Bluetooth app and see what is logged, and then find the functions that are responsible for handling the Bluetooth traffic. So you might think, well, all of this all of this seems a bit insecure. Why is all of this possible on this device? Why is everyone using it? Well, the ESP32 actually has a lot of features to improve the security of it. But as far as I've seen, not that many IoT manufacturers are actually using them. So if you discover any vulnerabilities and you end up reporting them to a manufacturer, you can recommend them the following. First of all, you can enable secure boot, which makes sure you cannot overwrite the code of the ESP32 with your own code, since the code is cryptographically signed and the signature is stored in a secure element. And you can enable the encryption of the flash, so you cannot simply dump it and reverse engineer it. For that, you will also need to disable bootloader flash encryption and decryption, because otherwise ESP2 will just encrypt and decrypt the flash on command. So that won't really help in that case. You also need to disable JTAG, and on the newer ESP32 devices, you can also disable the bootloader entirely. That's all I have to tell you for today. You can find all of the tools I used in this GitHub repository. I bundled everything together, so if you want to investigate your own devices, please have a look at it. If you find anything and want help with the vulnerability disclosure process, like I mentioned, you can contact the DIVD. And if you have any further questions, you can send me an email or find me around at this conference later. Thank you.